A very good morning to everyone. It's ended with a great pleasure. Once again, we welcome you all to the International Conference on Industrial Instrumentation and Control 2015. Today is the second day of our international conference, and the objective of the conference is to discuss the latest developments in the interdisciplinary field of instrumentation, provide a platform for the future developments of the same. So today we have other two keynote speakers, that is, they are Dr. Tom Lee. Dr. Tom Lee received his PhD in mechanical engineering in the field of control and automation from the University of Waterloo, Canada. He received his BSc and MSc in systems design engineering at the University of Waterloo. His technical interests include technology assisted engineering education, modeling and simulation, control systems and mathematical computation. In his current position as Chief Education Officer at CONSA, Toronto, Canada, he directs the product strategy and academic community development activities of the company. CONSA is the #1 company in the world for advanced teaching lab equipment for control systems, mechatronics and robotics. He also is an adjunct faculty member at the University of Waterloo and contributes to a range of research and education projects in the Faculty of Engineering. His past professional positions included Vice President of Applications Engineering and Maplesoft, Waterloo, Canada, a world leader in advanced mathematical analysis and modeling software, and Director of Business Development at Certicom, Toronto, Canada, a leading developer of advanced cryptography protocols and e-security solutions. His service record includes Industry Advisor for the Electrical and Computer Engineering Heads Association, Industry Advisor for M-Engineering Program in Mechatronics at the University of Waterloo, and Judge Advisor for the first robotics competition. So now I request Mr. T.S. Chandar to please felicitate Dr. Tom Lee. Thank you, sir. So now I request Dr. Tom, sir, so please address our keynote speech on the new phase of technology assisted control education.
Thank you, and very good morning to everyone. I would like to offer some additional thanks to the two previous keynote speakers, Dr. Bishop and Dr. Friedman from yesterday, because I believe they did a wonderful job in presenting some very different but complementary views of control systems. And in doing so, they actually helped set up for my talk very nicely. So I'm very thankful for them. Dr. Friedman talked about what marvelous things you can achieve if you focus on one very specific topic. In his case, it was sliding mode controllers. And if you work very hard and you're innovative in that context, you can achieve amazing things. Dr. Bishop reminded us that as important as that is, you also have to see the big picture and understand why we are trying to work with control systems and how ambitious we should be in thinking about what to do with our skills. So that's great, and both views are very important, but I'm a very practical man, and sometimes it's difficult for me to adopt either strategy exclusively. And for me, a lot of the work that I've been doing has to do with the convergence of those two views. how do you develop very deep, rigorous skills in control systems engineering, yet be able to see that big picture sufficiently so that you can achieve perhaps not all of the great challenges that Dr. Bishop was talking about, but get close to there, that it is a longer journey and to make good progress. So my title, The New Face of Control Systems Education, is really about that journey that we at Quanser have undertaken and that I have had some contribution to over the years. I have a unique job in that primarily I am a business person for the company, but I have some association with universities that keeps me connected to the academic world. Also, being a businessman, that means if you ask me difficult technical questions, I will not know the answer. I will defer myself the question to Dr. Bishop. So I think the good news is my presentation, I think, will be a little very entertaining and light for you. Perfect for a Friday morning just before the weekend. So with that as an introduction, let me introduce the company a little bit. Quanser is based in Canada, and we are a high technology company in the Toronto area. We're approximately 25 years old this year. We were founded by a gentleman named Jacob Apkarian. He is a very renowned control systems authority at a global level. He was the first to design a commercially viable version of the Faruta pendulum, the inverted pendulum. He also was the first to pioneer real-time, true high-performance real-time control on the MathWorks platform that you'll hear a lot more about with the next talk after mine. So in recognition of that and many other things, he was awarded with an honorary doctorate from my own home university, University of Waterloo, which is considered in Canada to be the #1 engineering university. Today we have offices in many places and partnerships in many places, including India, through our partners EduTech. What we do at the company, we're most famous for this. We make toys for old people like me. We make wonderful things that move and shake and provide you with an amazing way to validate the control systems work that you're doing. Many of you, as I saw in the sessions yesterday, are developing new algorithms for control. At some point, you have to validate it with experimental results. Many consider our systems to be the gold standard. So we support a wide range of different dynamics. So depending on what type of controller you're developing or what application domain that you're interested in, chances are high that there's something within our catalog that will support you. So in case you've never seen one of our devices, this is the kind of thing we do. So here's 4 examples. One is a very traditional servo motor butt connected to a little rail that has a steel ball, and it balances. We have things that look like helicopters so that you can study flight control without actually having to find a real helicopter somewhere, which sometimes is not easy to do. Magnetic levitation. The last one is an active suspension, which is a double spring mass damper system. Many of you are familiar with that from your studies. So these are wonderful platforms that isolate the essential dynamics that you need for your work. In addition to these types of platforms for research and teaching, we also have a fairly strong record in more advanced applications, typically with a strong research focus. So here's some examples. A lot of it's in robotics. So we're actually quite good at what's called telerobotics and haptics, which means using special devices that provide force feedback. We can control the motion of robotic manipulators that also send force information back to your hand. We also have mobile robotics of various sorts, and among many other things. A lot of these have been used in research applications in places like aerospace. We do a lot of work with the Canadian Space Agency, biomedical applications. We do a fair bit of work with defense, among many other things. So that's the research side. Like Dr. Bishop yesterday, most of my talk will be on education. So really, it will not be too taxing for you. Just sit back, relax, think about your own experiences as an undergraduate student. If you're a faculty member, think about the suffering that you have done in trying to do the best work for your students. And I want to offer you some food for thought, some things to allow you to imagine a bit more about where we can go from where we are today in a global sense to a new world. And I call it the new face of control systems education because of faces like these. So here's some new faces of control systems education. Certainly in my country and in Dr. Bishop's country, and many countries, doesn't matter whether it's North American or European or Asian, there's a lot of excitement happening within engineering education today. Here are two examples of technologies that took techniques that were essentially the exclusive domain of the best research labs in the world, and within about 10 years, they brought it onto the desktops of teenagers. So things like robotics, programmable robotics, and 3D printing, where you could not conceive of having a personal version of these when I was a student. It was just unthinkable. They would lock you up if you suggested it. But today, at least in my country, for under $1,000, many families, they are able to afford that. They can get a 3D printer. Why? Because it's fun. Robots, the little Lego robots, they're powerful computational platforms, and they, in our country, are about $100. Certainly a lot of families can afford that. And in the university setting, these technologies are making a big difference right now. Even in my visits to universities in India, many campuses have now started introducing some of these techniques, using them as platforms to introduce embedded programming, and among other things. And it's starting to come in different places. And certainly that's true in my country and in the United States. But there is a fundamental issue with that. And my prefacing comments about Dr. Friedman's talk and Dr. Bishop's talk kind of suggest what some of the challenge might be. When I reflect on Dr. Bishop's comments, he's absolutely right. We need to think big and think about real world. But if you actually think about how the courses are structured in typical institutions, there's a big problem with that. A lot of the great strides that we've been making with technology like this, with thinking like Dr. Bishop, is we've impacted a relatively small proportion of the total number of courses. That's just reality. Most of the courses that are given in most of the universities in the world are still largely a very traditional nature, where people like me stand up in front of a large room and we talk for an hour, and you listen and you go home and you do mathematics. That is the life of the average engineering student in the world. So what I wanted to really do for the past couple of years is see if we can expand that one piece, that wedge on the top. So whatever great thinking and exciting activities that we are introducing to improve engineering education, to see the big picture, it's affecting all of it, and without reducing the fundamental nature of those courses. So I am in no way suggesting that all of a sudden we should take a differential equations course and make it fun for everybody and just play in a differential equations course. No, those concepts are important. But there are things that we may be able to refine, to modernize it, to make it more relevant, and in the end, to actually make it more useful and more rigorous. So that's my hope. And a lot of the projects and techniques that I've been exploring start from looking at the current world that you are in and your research into control systems, which by and large is really good stuff, but it is reflective of a certain view of control systems. And that view, I wanted to start looking at whether that view could be improved if you look at what is happening in the world. And I'm hoping that the next speaker, because of the company that he represents, will give some insight into what's actually happening in a larger sense in the world, the practical world of control systems, because it's very important what he has to say, what I hope he says. But I'm going to just give you a glimpse of my view of that. So I'm going to ask you a stupid question, which is, what is control systems? It's a stupid question, but it's also a serious question. Anybody want to give me an answer to that? What is control systems? You know that? So some of you might say it's that. It's what's on the screen right now. It's some blocks with a feedback loop, and you have a plant, a controller, a sensor block, whatever. I mean, you look at Dr. Bishop's book in the introductory pages. That's a control system over there. And in fact, with the kind of research that many of you do, if you look through your papers and all of your references, you know, the total number of blocks will never exceed 2 hands, number of fingers on 2 hands. In this case, it's less than 1 hand. A lot of you do it with 1 finger, 1 block. To you, that's a control system. If I ask somebody who does high-end control systems in a big company, like an automotive company, like a Tata or Toyota or General Motors, and I ask them, what is a control system? This is what they'll say. First of all, there's no blocks on here. And in fact, to this day, I look at this thing and I say, how is that a process? Topologically, it's a V, and it says time goes this way, but there's 2 dimensions. Anyways, I'm not going to go into too much detail on this, but if you actually look at the specific parts of this diagram, these are the stages that people think about. And in fact, the word control doesn't even appear on that. And you only deduce that it is a control systems process from the bottom where it says implementation, hardware and software, coding and test. That's actually talking about the final deployment and application of the work that you do. And in fact, if you think about the work that you are doing and by that I am assuming certain things from reading the papers, the kind of controllers that you're developing, the kind of dynamics that you are considering, this is where you are. Somewhere deep inside that detailed component design, there is a place where you have to deal with the dynamics. So what does that all mean? I'm not for a minute suggesting that your work is small compared to a larger thing. All I'm saying is you are part of a complex ecosystem of concepts and processes. And the more you reflect on that, and hopefully the more you think innovatively about your own work in context of this large process, the better your work is going to be. It's going to be easier for somebody to pick the results of your work up and go forward with it, perhaps in a different application direction, perhaps in a more industrial setting, who knows. But ultimately, the definition of control systems are changing in the modern world. And a lot of my work has to do with, well, how can we actually reflect that in a way that doesn't disturb what we're currently doing, that doesn't throw away all the good things that we are currently doing or historically have done. Because in the end, a highly theoretical and rigorous approach, as was discussed yesterday in many of the Q&A sessions, the fundamentals and the theoretical foundations are absolutely important. And the reason why we focus on them at a university is because we're not training technicians, we're educating the future technological leaders of tomorrow. And in order to do that, we have found that people like this are quite important. So the foundations of what you are doing and what I have learned and what Dr. Bishop tries so hard to make sure that the generations of students understand is that the complexities of modern systems in terms of its dynamics are quite important. All of the famous names of science and mathematics, they have contributed incredibly important concepts. And if somehow you can take the work of these fine people with the reality of modern industry, with your own creativity, you mix all of that up, magic can happen. And really, in some sense, my work has been about making that transformation easier for institutions. Because not doing it ends up with this. So we have a situation where we have an incredibly motivated generation. The generation emerging out of the K-12 system today quite often have access to technology that were unthinkable 2 decades ago. They have a savviness about the world and about certainly technology that was unthinkable in generations past. And they with the best intentions, they sign up for university, they study hard for their entrance exams, and they get there, and then they get hurled off a cliff in first year. They get hit with the very theoretical mathematics courses, the likes of which, at least in my country, the difference between our final grade 12 education in mathematics and science and what you get in first year university, it's a huge difference, and a lot of students drop out. I know this is a big issue in the United States, where the dropout rates out of engineering are horrendous in many schools, where upwards of 80% of the students, very bright, young, motivated students, never finish, not because they're not working hard, it's such a shock, and also I think, as we'll talk a little bit later, it shatters their view of their dreams of engineering. And when your heart breaks, it's very easy for you to make poor decisions about your career and go somewhere else. So what can we do about this? And so I'm going to offer to you in the next little bit what our company's proposition is. So I don't have answers, but I have done projects to try to explore this big issue. And I'm going to offer 3 interesting examples for you. And in the end, what we're trying to do is harmonize the various aspects of technology, the exciting technology that we have today, which undoubtedly it has some motivating aspects for students, with the very important requirements of high education that all of us aspire to. So how do we harmonize those things? How do we harmonize fun with math? So unless you're a certain type of person, those 2 words do not go together. Fun and mathematics typically do not go together. At least with me, it doesn't. Maybe some of you it does. Based on your papers that I've seen, I suspect for some of you mathematics is fun, but certainly with a lot of students it isn't. I look at it in 3 ways. You have to do 3 types of activities to make all of this work. First is rigor, and this, again, is a statement that I do not want to under stress. It is so important that we do not water down the core concepts of what we do. So in the end, the students must still be able to understand the nature and the rationale behind a differential equation-based model of a physical system. They must understand the nature of numerical simulations to solve those equations, nature of experimentation and validation. All of that good stuff they have to know. But what I think has to be added to that is some element of creativity. Engineering is inherently a creative profession. I don't know if for those students in the audience, maybe some of your professors have told you that. In my education as an undergraduate, I was told that many times. It actually never made sense to me, because as I was sitting there solving equations 24/7, and people are saying, oh yeah, you're in a creative profession. Excuse me, maybe I don't understand the definition of the word creativity, but it doesn't seem like that's what I'm doing. So really, I think as we are making sure that rigor is established, we have to be vigilant about staying true to the notion of engineering being a creative profession, because it absolutely is. It's not creative in the sense of an artist or a musician, but it's creative in the sense that you are taking a whole pile of unusual, complex things and making something wonderful out of it that people can benefit from. Finally, to make everything kind of interesting and work well for a young person, and looking at India and the young people riding around in motorcycles and looking at the advertisements, The young people of India are not that different from the young people of Canada. I have a 19-year-old son and a 17-year-old daughter, and I have some sense of what they're interested in the world. Again, mathematics is not one of them. They're interested in all sorts of things, and they're interested in trendy things. So I do believe that we have to be observant of the trends of the modern world. Those are the three dimensions. And over the past 3 or 4 years, we've been working with a whole range of different universities and different types of systems to explore this harmonization. Several of them are in Canada. Dr. Bishop's university is on there because we're starting to do a new project involving different ways of delivering the concepts of controlled systems. I also have a strong affiliation with the University of New Mexico in the US, and even companies like National Instruments are part of our collaboration to look at new ways of treating control systems. So I'm going to show you 3 examples, and I've given them kind of interesting titles. And these are titles that you would typically not associate with control systems courses. But I just want you to start thinking about these titles. Not so much so that you better enjoy my presentation today, but I do think it helps you see the big picture. On the bottom left, the gamification of high-fidelity engineering models. So you'll see what that means. From classic control to complex mechatronic design. And on the top, one that's particularly dear to me, the magic of modern robotics. And that's dear to me not because it's about robots, but it's because of magic. I am still a child at heart. Maybe you haven't noticed that, but yeah, I believe in magic. I think most students want to believe in magic. I entered engineering because of magic, and I think if we do our jobs right, we can maintain that sense of wonder and the grandness of engineering for our students. So let's start with the gamification thing, and we'll work up to the magic part. So this is one of the very first interesting projects that we started. So in terms of the rigorous part, we wanted to make sure that, the kind of things that we've always taught in control systems in terms of the system dynamics, the modeling side, and actual developing controllers, and yada, 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 all of that is done. We also wanted to add an element coming from the gaming world in terms of computer graphics and some ability to work with control systems in a way that feels like a game, and you'll see exactly what that means. And finally, because it's a game, we just presume that students might enjoy the process. So they won't know that they're actually learning something very rigorous and analytically deep. So underneath this is the notion that traditionally we have supplied these devices to professors who then do demonstrations where students use them to learn about control systems like PID control, position control, speed control, things that many of you are familiar with if you've ever done real experimentation with control systems. But in some sense, that's what we've always done, and I was wondering, can we do this in a slightly different way so that you end up with the same level of insight on the analytical aspects, but it actually has more applicability. So this is what it is. It's kind of hard to see initially, but there are 2 DC servo motors. The one on the left has a disc spinning pretty quickly, and the one on the right has the disc sort of going back and forth. And as you saw the finger touching it, you can add disturbances and whatnot. Those are classic control systems. The one on the left represents an application of velocity control, the one on the right position control. Not too different until you notice that there's a steering wheel attached to it and a pedal. And on the screen is like a driving video game. The models to that video game are attached to those motors. They are in a true hardware-in-a-loop simulation. Why is that important? Okay, aside from the obvious that maybe a student might like driving this game-like thing, the fact that it is in a proper hardware-in-a-loop simulation means that there is an ability for you to discuss why you might want to test with real hardware for a control application in automotive. In fact, this actually is conceptually not a game. If you go into a real automotive company, as my friend Antonin knows full well, you go into a car company, this is what they do. They have large rooms with big computer screens of car animations and steering wheels and big, huge motors and things. And they try to map visualizations of the final application onto their controller. It is out of the question that if you are a new engineer for Tata and you work for 7 weeks to come up with a new controller, they're not going to let you put it inside a real car and have it drive around a test track. They're going to put it on a simulator like this, but not a pure software simulator. They're going to put it on something that has a little bit of hardware to it so they can see how it will kind of work in the real world. So what we've done was we've taken traditional position and velocity control, not too different from what you would actually do in 10 years ago, but made it more interesting and fun. Interesting in the sense that it's industrially relevant, fun in the sense that it's a video game. So at a more abstract level, this is what it means. So in that case, the software was LabVIEW. This is what you would have done 5 years ago. If you had purchased one of our machines and you wanted to do a hands-on lab, this is what you would have done. You would have hooked it up to a piece of software, LabVIEW or Simulink. You would give it abstract signals, steps and ramps and things like that, and you would look at the response. And then you would change or add disturbances and see how the reaction is. You would try to tune it. You would explore different types of controllers and all of that. Many of you have done that, no big deal. All we've done with this example, with the automotive, is we added a second motor because we want to show speed, that's the wheel dynamics, as well as the position. But in addition to the traditional learning objectives, we added a lot of insight into applications, sensors and encoders, model fidelity, and the importance of modeling, which is a very, very important topic, signals, filtering, even human factors. There's a lot of potential here for you to really look at system-level issues. If you look closer at the software side, again, this is LabVIEW. There is an entire equivalent within the Simulink world. The systems, because of the nature of these graphical design, graphics-oriented, block diagram-oriented design systems, you can easily carve out or separate the subsystems and really talk to the students and have them understand that the control systems belong as part of a larger application, and all of them are important. And one of the things that makes a great control system versus just a theoretically sound but perhaps not a very useful one is its ability to exist in such a large system. So this is a quick example of one of the projects. And right now, it's so early, there's only been a few universities that have tried to deploy this, but ultimately the hypothesis that we are testing with this application are things like 10 real-world applications. Can we actually throw in the concept of automotive engineering inside a control systems course and not confuse the heck out of everybody? I think if you actually put in real automotive concepts in there, you will confuse everybody because they take into consideration so many more factors. So what we are saying is, let's take out the essential concepts, put those on top of traditional control systems concepts, and will that help people? I don't know. We'll find out over the years, next few years. Are video games good for students? So that's a pretty important question. And I think if I just ask the faculty members here that question without showing this, are video games good for students? Many of them would say no. No, we should make sure they don't play video games. But in some sense, I think because of the natural instincts of young people, and in this case, because this is what industry does, it may be a good thing. Something for you to think about. So let's move on to the next one. This one is really important to me because before I started working for Quanser, I was a lot like you. My view of control systems were those 3 blocks that you saw in the earlier diagram. That's what I thought a control system was. But when I got to the Quanser company, where we were actually building real machines that were working on top of rigorous control systems, I finally had a better understanding of why we taught those concepts that all of you are so familiar with. And quite often it pointed to a more recent field called mechatronics. That too has many different definitions, but loosely I look at it as techniques in engineering that, where we use computers, quite often very small computers, to control the behavior of physical systems, and the actual computational techniques and the mathematical techniques that we use to do that. So it is more than looking at the dynamics and analytically deriving the controller. It is taking into account all of the different issues that you need to make these practical. So how do we go from control systems to mechatronic design? And well, first of all, why do we want to do that? It's because mechatronics is the natural destination for control systems. If ultimately you work on your control algorithms and you just stop and do not think about where it's going next, then it will at best be a good theoretical exercise. You will publish your papers in good conferences like this, maybe get into graduate school, who knows, but that work will end up nowhere. I'll be honest, it will end up nowhere unless you start thinking about the mechatronics dimensions to it. So we were wondering, can we bring some of the essential ideas of mechatronics into a control systems course, again, without turning the world upside down and making a huge amount of additional work for people? So we started looking at things like this. So this is an example of one we did with National Instruments. Again, we took one of these servo motors, and in this case with an inverted pendulum attachment. And on the other side, we attached it to a Kinect motion sensor. You may be familiar with those from the Xbox system. They're really good, nice sensors. We have a traditional computer for development, and we have this thing called a MyRio, which is an embedded platform. A bit more of a higher end one, and it's something that National Instruments, have offered to give you a view of embedded systems that is very consistent with a lot of teaching activities at a university. In any case, we're wondering, can we actually get the students to start attaching sensors and things to servo motors within a controls course, and will that be a good thing? So to test that, we actually hired an intern. So that's William. He was in grade 11 at the time. Now, he's an exceptional grade 11 student, but he was a grade 11 student nonetheless. And we said, all right, here are the basic concepts of control. And we didn't go into too much of the detail, but we said, take this motor, this basic idea, and see if you can hook up a sensor to it and have it understand something and do something with the motor. So we used words like something a lot because we wanted him to sort of think about it and come up with the application. So I'm going to show you what he ended up doing. And this is sort of the connection of it. So here you see this servo motor right there. And the software, again, is LabVIEW, and there's a little picture of a human being. And here's the Kinect sensor. So that's going to sense the motion of arm swinging by William, and that's going to define the input signal to the inverted pendulum. So let's see how that actually works. Okay, so he's swinging his arms, and as you can see the pendulum swinging back and forth. It's actually doing a proper swing up, and then it balances the rod. And he's actually moving back and forth right now, and you can see then the input signal to that pendulum. Is this practical? No. Do people do this at Tata? No, they don't do this. Do the people at Tata attach sensors to a physical system? Absolutely they do. Your modern luxury car has sensors everywhere now. Everywhere. So the technique of being able to sense something from the physical domain, do something with it, and then use that as in a feedback loop to do something else, that is absolutely an industrial process. For William, it was just fun. And he spent about 2 weeks doing this. We were absolutely astounded by what he was able to achieve for such a young person. So, discussion points. So we've just taken in fact, in both examples, a simple servo motor, and we've made it really complicated. Is that a good thing? I think it is. I think you can understand the fundamentals of PID control better by adding more stuff to it and making it more challenging. But the challenging aspect of it is a good challenge. It's a vigorous challenge. It's intellectually stimulating, and most students, I think, will respond well. And we are really moving away from a very narrow view of control to something that is more comprehensive. Here's another one. This is fun. That's all it does. So you see the servo motor? It has this weird arm, and it can shoot a ping pong ball and land it in a cup. Okay. So I don't know if some of you have done things like this before. When I was in high school in grade 11, we had a physics project where we had to use some calculations, kinematic calculations, to shoot a ball and hit a target. That's not hard to do. Creating a machine where you can just set the distance and say, give me 1.78 meters and have it hit it, that's much harder. That's what this machine does. It does a few other things. So in fact, initially we had a very simplistic view of this, which is 3D printers are now the hottest thing in the academic market. Let's do something with it. That was it. That it was as innocent as that. We wanted to play with 3D printers. But in the end, because we were Quantzer, and part of our approach is always, we don't want things just to do stuff. We want to make sure that the precision and the power of mathematics and modeling and the conventional rigorous approaches to engineering are highlighted. So we wanted to identify an application where precision matters. So in creative thinking, we were thinking about golf swings or catapults and projectiles, but there's actually a popular game in social situations in North America called Pong, beverage Pong, where you basically throw a ping pong ball and try to get it into a cup, and students spend hours and hours doing this, and we thought, let's make the world's greatest ping pong or Pong player. That's kind of where this came from. But the more serious aspect of this, what you just saw, is once again, you had traditional velocity control, but we also added to it some elements of embedded programming, projectile kinematics, experiment design, and CAD-based rapid prototyping techniques. Once again, we took the kind of work you're doing in control, and the way I like to express it, we place it inside a proper engineering workflow. A workflow is another word for process, but it's closer to the kind of words that industry uses. And it just means a recognition of the fact that your work has to go somewhere. And it has to go somewhere good. And we were able to introduce students to a good place that control systems can go into. And in this case, rapid prototyping, embedded programming, and ultimately projectile applications. This is part of actually a sequence of student projects, and this is the latest version of this. This was what came out of the University of New Mexico this year. The Rube Goldberg machine is a formal concept where you devise an incredibly sophisticated machine that does nothing. And in fact, it's even better than that. If it does something, for example, pick up a cup, it has to do it in the most mechanically complex way possible. And what it is, it's a test of somebody's ingenuity in connecting mechanisms. So we gave a challenge to the students saying, we are going to give you 2 servo motors, one up here and one down here. You have to design and fabricate something with a 3D printer and then create a machine that sends a ball in all sorts of wonderful ways, and understanding all of the physics and the mathematical modeling required and robust manufacturing and all of this good stuff. And you have to create it in a self-contained demonstration version, meaning there has to be an ability for it to do its task and reset. And what you just saw is the reset mechanism of the ball being thrown up. So this was a 4-month project. These students have never seen our servo motors, and they were able to do the fundamental research they needed to control the motors. And then it was pure mechanical, electromechanical creativity and experimental design after that. So, that's kind of fun. What are the serious points behind this? It's not too entirely serious, actually. 3D printers are so cool. You do anything with it, and it's going to interest students. That statement is actually one of those things where, yeah, everybody is now intoxicated by 3D printers. They are so amazing. If you don't do anything with it as educators, then at best, you will miss an opportunity to do something interesting. At worst, you will be really out of sync with the technology of today. Especially in engineering, the techniques of rapid prototyping embodied by 3D printing technology is a very important technique that is emerging, and your students will be at a deficit. I'm not saying control systems is the only place to teach it, but to be able to reflect that kind of reality in multiple places within the curriculum, I think, is an important topic of consideration for you. Overall, just the whole notion that none of these had real applications other than a vague connection, is that a good thing? Or should we actually tie it explicitly like what we did with the automotive? So that's also an interesting point of discussion. And I make these points of discussion not because I have any answers, but these are the things that I think about. So I'm going to go to the final one, which is the magic of modern robotics. And again, let's emphasize the magic. So I'm going to ask for a raise of hands, but how many of you are in engineering because there's something really exciting about it, and there's something that you saw in the real world that you said, I'd like to be the one that makes the next one that is better than that one? How many of you went into engineering for that reason? Okay. Enough, and everybody else is just asleep. I certainly went in because of that. For me, I love telescopes and outer space. And it was not so much going into space because I'm a coward. I don't want to go into space, but I like looking at space, and I like the machines that look into space. So when I was a kid, we didn't have computers. I built a telescope, and I stayed up all nights and looking at stuff that I didn't understand. But I loved the machinery and the optics of the telescope. It was magical to me. And there were other things like that. And I'm sure for many of you, you can tell me the same story. So a lot of us go into engineering because we fall in love. I want to show you a little video of a love affair I had with a robot once. So this is Wabian. This is about 15 years ago. I was in Japan visiting one of the premier engineering universities, Waseda University. This gentleman named Professor Takanishi, who is one of the foremost experts in humanoid robotics in the world. And this was his lab's creation, Wabian. You've seen Asimo from Honda, right? The little white robot does stuff. That's Asimo's cousin. If you look at Asimo, one of the things that you notice, he sort of walks like this, as if his hips are fused together. If you look at the way Wabian walks, he sort of has this thing going. It's almost like a dance. They added additional degrees of freedom and the control out. They did real control. That's kind of stuff that you're doing, but it's inside this magical thing. And I thought, no, it's absolutely possible to connect what you do to magic. But if you think about what universities are doing today to deal with this magic, many of them are doing this. They are using some of these hobby platforms. There's nothing wrong with that. I mean, these are actually very powerful, capable systems. But they have a particular view of robotics that I would like to challenge as being not optimal for doing this. If you actually want to prepare yourself, or if you're a faculty member and you want to prepare your students ultimately to be able to do this and to work at the Takanishi lab among the many others doing such exciting projects, there's a whole bunch of things that you have to have a better understanding of. You don't have to be an expert in everything, but you have to be aware of everything and be expert enough in a few of those things that you can be a part of the team. And ultimately, it's because, once again, the dynamics, precision, and complexity actually matter. And so more recently, at a company level, that's what we've been focusing on. In this emerging world of robotics, which is really, really hot right now, what is our role as Quanser and our philosophy of Quanser? What is our role in that? So we have to look at a little bit about what robotics means in the formal sense as far as the academic world is concerned. Actually, we tend to divide it into two worlds these days. One is the traditional world of manipulator robotics arms. And we have that's filled with things like Donovan-Harkenberg matrices to develop equations for the kinematics and similar types of really intense mathematical techniques. And then we have the more recent infatuation with mobile robotics, whether they're ground vehicles, aerial vehicles, or humanoids, robots that sort of look more like what you would see in the movies. And that's probably why people are getting excited about it. But now at an academic level, both views of robotics have found a foothold, and people are doing some good work with it. What we wanted to explore was how to do that really, really well because of a very important reason. There's a third branch of robotics emerging, and that is hobby robotics. And in fact, the next talk, I think we'll talk a little bit more about that. At least in North America, we have a weird situation happening. So in my biography, there was a little mention of something called First Robotics. That is a national or an international competition. Approximately 5,000 high school student teams, and the ages of the kids are anywhere from grade 10 up to grade 12. And they develop complex, autonomous, and mobile robots. And the level of sophistication is very high. And in fact, they do apply these types of activities. And they come into university understanding PID control and embedded programming and actuation and control. They know all that stuff. So the question is, how do we hide from it and how do we suppress it because it's kind of different from the way we teach robotics, but how do we take advantage of it so that we do even more? And ultimately, how do we prevent this and go more towards a much more enlightened view, an integrated view of robotics? So this is more of a commercial pitch that I'm going to make, that the work that we're doing in Quanser is actually trying to figure out how to divide our product line into three categories. From right to left, let's go backward. We have some mobile robots, and I'm going to show you a little video of one soon. We have ones that fly, we have ones that roll around on the ground. We also have traditional arms with haptic interfaces as options. So that's to really look at the kinematics and dynamics of manipulators and the control of their motion and all that good stuff. And for those who want to do robotics applications, but they really want to focus on the control. So let's say you're doing flexible manipulators or doing something like that, that requires more sophisticated control algorithms. We isolate certain types of dynamics for pure robotics-oriented control applications. So those are our products, but more importantly, we're now commercializing versions that are very well suited for undergraduate education. So this is a very significant point. Right now, robotics education at the undergraduate level is dominated by things like Lego or Arduino or the hobby robotics platforms, because that's how we as academic worlds have responded to the hobby trend. But ultimately, through work like yours, all of us want students to be able to do what I would call real robotics to these higher end applications, the pictures that you see in front of you. That requires the study and mastery of a whole range of different topics. Hobby robotics simply do not have the dynamic fidelity to let you do that. So we're introducing a whole range of new robots. So this is one of the examples. This is called a Q-bot. These are the kind of things that we allow you to do. And if you look at the actual robotic applications, this is the real thing. If you can figure out how to do this with software, and right now for this one, the software is MATLAB and Simulink. And that's an amazing platform for you to really look at the concepts of robotics without going into deep, dark C programming, which will just overwhelm any course, and allow you to really study modern robotics. So we're trying to figure out, how do you get a proper, sophisticated, high-end robot at an affordable price that you can actually deploy to an undergraduate class? Our partner in the academic world is the University of Toronto. This is Dr. Tim Barfoot. And ultimately, he wanted to be able to do real robotics at an undergraduate level using Simulink in his case, with no programming in ROS. ROS is the robotic operating system. That's what the final practitioners of robotics use these days for real applications, but it's so intense and dirty, it will never be applicable for an undergraduate course, in his opinion. So he wanted to find an alternative, and he chose Simulink for that. And ultimately, he also believed that he didn't have time to just try to build it himself. I saw an example of the University of Bangalore where they were doing that, and it's been taking them years to refine it to a certain extent. And depending on how, what your budget is like, getting a proper commercial platform quite often is the cheapest way for you to do this. And that's the direction we were heading. And ultimately, it was really about fun plus rigor. Does that equal magic? If you had access at the undergraduate level to a real robot like R2-D2 that can go and sense obstacles and go around it, pick up stuff, whatever it is, would that rekindle your love affair with engineering that got you there in the first place? That's the hypothesis. So in the end, again, these are works in progress. Maybe I'll come back in a couple of years and report to you how we're doing. Discussion points. Is this a good bridge between hobby robotics that students are now coming into university with and real-world robotics? How far can we push this? So you've heard of the Internet of Things. This view of robotics is reflective of the fact that robots are platforms. They're not final applications these days. So just as the microcomputer of the 1980s provided a platform for engineering creativity where magic happened, then following that, the World Wide Web and its view of applications, then mobile platforms. This is the next one. Things that actually move around, physically move around, but are smart computationally. We don't know what they're going to deliver to the world in a few years, but they will. And this is another form of introducing that in a rigorous engineering fashion. So to conclude, this is part of a long process, just like my talk is part of a long process. This picture is actually a real picture. So this is, these are my notes when I was a teaching assistant for our controls course at the University of Waterloo. I found it the other day. Oh my goodness. And based on what you see here, you can tell how old I am. This is a bit of a confession. So I was part of the instruction team for this course, and it was not until I took my job at Quanta that I fully understood what that course was about. And really that's why I'm doing this talk today. So as somebody who was on his way to a PhD at the #1 ranked technical university in Canada, I did not know how to properly deploy a control system because even the lab was so abstract. All I knew how to do was, okay, I know it's this equation, I know I programmed this little bit, and I push these buttons, and this happens. That's what I knew. And it took another 20, 25 years for me to understand why that was important. What I was hoping to do today was give you a sense of why your work is so important, and have you think beyond that final conclusion that I've been seeing in the sessions. And they're really important because you've worked hard on those algorithms, but in the end, to think about where do those algorithms go. And ultimately, they go here. They go to real people, real excitement, real magic. So really, we're talking about going from an old face like Sir Isaac. Everybody knows him, everybody loves him, but we want to really make him cool again. So, yes, your work is important. I've really enjoyed being here. I've enjoyed meeting everybody, young and not so young. And I still have another day, so I look forward to another exciting day here at the conference. Thank you. Any questions?
Any questions?
If I talked about LQR, would there have been questions?
Tom, it was a very nice talk. Why? Because I'm teaching control from last 15 years, and you change our view definitely. And definitely your concerns anyway, it's a set up a lab, the center of excellence in instrumentation and control department, the only COE in India, and definitely it's enlightens. So how to proceed and to teach a control system. Specifically, I commit, definitely, I will try to move this way. Thanks very much.
Yeah, and if I could make a follow-up comment to that. So Dr. Shenge referred to the Center of Excellence at this institution. So we are collaborating on developing better ways to teach control systems. And so these techniques we would absolutely be willing to share with you. And in fact, at some point after you recover from this conference, we should have a follow-up conversation on some practical ways that we can get some of these ideas going here.
There are no questions. Thank you, Dr. Lee, for exposing us to a new dimension. I hope everyone will agree. It was a thought-provoking speech, and he has introduced us to a new, different dimension of how to teach control systems in a much better way. Thanks a lot. As usual, we will give him a big hand